All right, so let's talk about graphs. So there's no lecture test for today. The lecture test will be on Wednesday's lecture. That's what you need to know to continue with the project to get LT5, LT6, AO1, and AO2 you can actually do with what you know already, though it is pretty tough to do. What's the bribe? I don't know. Oh, so just so this makes the YouTube video, fill out your course evals. I'll have some sort of bribe for them. I don't know what's going to be yet. But if you're not aware, just a quick recap, the course evals, the only piece of information I get about those before the grading deadline, like after the grading deadline, I can read all of your comments and everything. Before the grading deadline, the only piece of information I get is the percentage, the completion rate, the percentage of you who have actually filled it out and submitted it. I don't get any other piece of information. They do that so your feedback doesn't affect your grades at all. It literally can't, because I have to submit your grades before I start accessing that feedback. This also means that whenever I want to bribe you, because I want the feedback, I want you to fill out the course evals. When I bribe you, it all has to be based on percentage of completion rates, submission rates. I forget what I call them. Submission rates, I guess. So based on how many of you actually fill out the thing, I'll have some incentive. I just don't know exactly what that looks like yet. But fill it out. If you fill it out now, you don't have to worry about what my exact incentive is. You'll just be closer to getting it. Free pizza. Yeah, maybe hints. Hints on AOs, maybe. And I already, what I should have done is I shouldn't have waived one of the LTs for the last project. I should have said 6 are required, and then my incentive could have been going down to 5. I don't know if I want to go all the way to 4. I don't know, maybe. And then hints on AOs, something like that. I'll think about it. We'll be talking after lecture. We can brainstorm. Bonus AO. There's already 12 AOs though. If you can't find 6 of those that you're gonna do, is the bonus AO really gonna help you? Here's 13 options instead of 12. Like, I just don't think that's gonna help anybody. I might. So here's what I'm thinking, and we got to get to some content here. Here's one thing I'm thinking is letting you submit one of the previous application objectives for credit again. So there are quite a few of you who were very close on an application objective, but just didn't finish it by the checkpoint. And you have that code sitting there very close to completion, but you just didn't get credit for it. I might say, okay, you can get credit for 1 AO past the deadline. That's one of the things I'm thinking of. Yeah, your GA will see the light of day. I'm leaning towards that. So I'll probably end up doing that as at least one of the incentives. All right, but let's talk about some graphs. And before that, let's talk about some other data structures. So we've seen several data structures so far. Or free quiz interview grade. I don't like that because that's like removing one of the learning objectives of the course. That's like, those are things that you have to know to proceed with computer science. If I waive one of those, it's like saying, you know what, just kidding. You don't actually have to know that stuff. So I'm not a fan of that. If I do anything with the quiz interviews, I'll let you know. But let's brainstorm after lecture. Let's get some juicy content out there. So we've talked about these data structures. We've seen arrays. You've seen linked lists. These are both sequential data structures. You have data, linear data stored in order. The order matters with both of these in one way or another. We also had key value pairs where the order doesn't really matter, but we don't want to just map things based on their order. We want named keys instead of like indices or just their position in a linked list. So we had key value stores, which are mapping some value to another value, and the order doesn't really matter here. These are your dictionaries, your objects, your maps in the 3 languages that you've seen so far. And then we introduced trees. This is our first non-linear non-associative data structure, where key value store is an associative data structure. A tree lets us represent information with more structure to it, where the actual structure of the data structure changes its meaning. If we change where these nodes are, it actually changes the meaning of the data structure. And we represented different data with this. We can't, for example, it's very difficult to represent an expression tree as either a key value store or a sequential data structure. It'd be very difficult to represent that information. But when we represent an expression tree as a tree, it becomes a lot easier. Why does Ruby name maps as hashes? Maps are usually built on hash maps. So let me introduce a type of data that's going to be difficult to jam into any one of those data structures that we know. So what if we had a data structure where we have a lot of nodes that are connected to each other? For example, if we have intersections and roads connecting those intersections, how would we represent this information in one of the data structures that we have? Or what if we have the same idea but with train stations and connections between those stations? Or this image, which we'll actually look at in depth, the early days of the internet, where these were the servers on the internet and they were connected, shown by these lines. How are we going to represent information in this style in a data structure that we have? So I think it's fairly clear that the sequential data structures aren't going to really represent this, and the key value stores won't. But we do have one data structure that kind of fits this structure. So let's give a try. Let's try trees and try to represent this type of information using a tree. So, and let's take this map. This is the one that we'll be working with throughout this lecture. This early graph, not to spoil, but this early map of the internet, it's still a bad word because that sounds like the key value store of a map. But this, I don't know, this internet, let's try to use a tree here. So we're going to start at one of these nodes in the internet. I'm going to start at UCLA right here. And instead of having just a left and a right child in the tree, I'm going to have multiple children, as many as necessary, to be able to represent this information. So I'm going to have each child of a node be all of the other nodes that can be reached through that child. So UCLA is connected to Stanford, SRI, UCSB, and RAND. So we have these connections all from UCLA, and we'll build our tree this way. And for each connection that we have, we're going to do the same thing over there. So we went to Stanford. Stanford is connected to SRI and UCLA. So Stanford is going to have children of UCLA and SRI. And we already run into a big problem here. We have duplicates in our data structure. Duplicates itself, bad, but not the worst thing that could happen. But what happens when we get to this node, UCLA? And we say, okay, what are all the children of UCLA? Those are the connections that UCLA has. Well, that's Stanford, SRI, UCSB, and RAND. Those are all children here. Well, that's the same thing that's going on here. And we're going to go infinite. We're just going to keep building this tree. Okay, the children of this node, the children of this node, the children of this node. And in short, what we have is what we call cycles, where we're going to keep running around in circles, where Stanford has a child of SRI, has a child of UCLA, has a child of Stanford, has a child of SRI. And we're going to keep going around in those cycles forever, or we're just going to ping pong back and forth between every connection. So a tree, as we've seen it, where it's strictly all of the children are the nodes that are connected to this node, isn't going to work. We got away with it with trees because we never had cycles when we were talking about trees. But with graphs, do you cover graphs in 191 now? I think you do, but in a slightly different context. Is the same graph in CSE 191? Oh, good. This is going to be an easy lecture then. Yeah, if they talk about graphs, they're talking about the same thing. Cool. Yeah, and specifically in 116, we're going to talk about undirected graphs. That's right. So we're going to talk about undirected graphs. You just covered them. Fantastic. So let's try this again, except whenever we're going to add a duplicate, we just don't. We just don't add the duplicates. And now when we do that, UCLA doesn't quite have children anymore. We're not going to use the terminology of a tree. We're going to say UCLA has edges connecting UCLA. And by the way, I realize not all of you are in 191, so I'm still going to cover this the way I would, as though you're brand new to graphs. So don't panic if you're not in 191. So UCLA has edges connecting it to these 4 nodes. And when we get to Stanford and we say, okay, Stanford is connected to SRI and UCLA, we're going to realize that we already have the connection to UCLA and not re-add it. But we will add SRI because that's a new connection. SRI already connected to UCLA, so we're going to connect to the node that already exists with that name. We already added SRI to the graph, so when we add that connection from Stanford to SRI, we just connect to the existing node when we're connecting to it. Yeah, just don't. If there's something that's causing a problem, just don't do that thing. It's pretty simple, right? So what we end up with is a graph data structure. This is our new data structure that we're talking about, where instead of like starting at a root and then having children and going down the tree like we did with trees, now instead we have a kind of more unstructured data structure, if that makes sense. I don't know if that came out right. But we have, it's harder to visualize these aside from like the actual physical map in this case. But we have a list of nodes, and we have connections between those nodes. So we don't have like UCLA has these children. We have UCLA, Stanford, SRI, UCSB, Rand, SDC, Utah. Do I really want to go through all of them? These are the nodes in the graph. And then separately, we have the connections between those nodes. There's a connection between UCLA and UCSB. There's a connection between Utah and SDC. There's a connection between Case and Carnegie. And this information here represents the same exact information that we have over here. Except when we visualize this, I'm going to show you how to represent this in our code. So now we can have cycles in a graph. This is, when we're looking at the theoretical definitions, this you probably did cover in 191, the difference between a graph and a tree, mathematically, is that a graph can have cycles. A tree, by definition, cannot have a cycle, where a cycle means you can get from one node, you can start at a node, and travel along nodes and get back to that node without ever backtracking across an edge, without duplicating an edge twice. So here we have a cycle right here. This is a cycle. This is a cycle. This is a cycle. We can't have any cycles in a tree. Once you have a cycle, and if you have a tree and you introduce a cycle to it, you no longer have a tree, you have a graph. And you can go up in a graph. So that's what I mean. That's what I was trying to express. You can go up in a graph, but more meaningfully or less meaningfully, there's no meaningful up and down. Like a tree, we draw the root at the top and then the branches come down. In a graph, there's no real way, there's no like visual way to represent a graph. Like I could have all these nodes up here, these nodes could be over here. I can rearrange these nodes any way I want. It's still going to be the same graph. There's no sense of up, down, left, right in a graph. There's just nodes, and those nodes can be connected to each other through edges. No sense of direction, right? Yeah, there's no sense of direction in this graph. Visually, for this specific application, if we look at the map, yeah, there's direction. When we represent this as a graph, we don't care about the direction. We're not trying to be geographically accurate with the graph. There's just no sense of direction with the graph. So with a graph, we have to be careful about our algorithms. We can't use our tree algorithms just straight out of the box. We can't use our tree traversals. because we're going to end up in infinite recursion. We're going to traverse. We're going to start here. Maybe we do an in-order traversal. We make a recursive call. 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 Make a recursive call. And we've gone infinite already. We're just infinite right from the bat. If there's a single cycle in the graph, we're going to go infinite in our recursive calls. So we have to generate new algorithms to deal with this type of data structure. Before we get to those algorithms, we want to talk about how to even represent a graph in code. And we're going to represent this a bit differently than how we represented linked lists and trees. So linked lists and trees, we had a node class, and a node had references to the nodes to which it's connected to. We don't quite do that in graphs. I mean, technically we could. There's nothing stopping us. But we just don't, because that's not how, it's not how we've done it in computer science for the past 50 years. With graphs, instead we store the edges and nodes in certain data structures with certain structure. There are two primary ways to represent these, which you've probably talked about for those of you in 116. Or 116, I hope that's most of you. In 191, there are adjacency matrices and adjacency lists. We're gonna, what's 116? We're specifically gonna use adjacency lists in this class. So what we're going to do is store a data structure of all the nodes to store what the nodes are in the graph, and then a data structure mapping nodes to each one of the edges connected to that node, which will make more sense on the next slide. So to store this graph, we would have one data structure, not shown here, which will just store all of the nodes themselves. And I have that data structure, actually this is all you need, but I have that data structure in the code specifically. In the examples repo, I have a graph and a BFS algorithm in the code that you can use in your homework. Excuse me. The graph is actually given in the homework handout code as well. I have a data structure, which is a map of the nodes, mapping a unique node ID to that actual node, what it is. So for this graph, I have a map mapping ints, which is a unique ID for that specific node, and maps that to strings, which is the label for that actual node. How we really represent all of the information of this graph and all the structure of it is through this adjacency list. So the adjacency list is going to be a map, or some key value store in general, mapping each node to all of the nodes that are connected to that node through an edge. So UCLA is connected via an edge to Stanford, SRI, UCSB, and RAND. So in the adjacency list at UCLA, if we look up UCLA, we expect to find those 4 nodes that are connected to it. If we pick MIT, we expect Utah, Lincoln, BBN. So if we look up MIT, Utah, Lincoln, BBN, it's a map. It's a key value store mapping each node to all of the nodes to which it's connected via an edge. This is the representation we'll use in 116. In other courses, you'll see also adjacency matrices, which is a matrix where the rows are the rows are nodes, and the columns are the same nodes, and there's either a 1 or a 0 in each cell in the matrix, representing a 1 if there's an edge between those two nodes, and a 0 if there's not an edge between those nodes, or true false if you want to use booleans. And then you look up, is there an edge between these two nodes? You look up, okay, SDC and Utah, and then you see if there's true, false, 1, 0, however you're representing your edges in that matrix. We're not going to talk about adjacency matrix in this class, but that's the other way, the other primary way that we represent graphs. And they each have their advantages and disadvantages that you might not care about. I don't know if 250 cares about that, but in 331 you certainly will care about the differences between those two because they both have different performance implications. For 116, adjacency list, and we're calling it a day. We're just going to pretend every graph's an adjacency list. So in this is the graph code. I have a graph of A's, whatever A is. Whenever I want to add a node, I'm going to assign a specific index to that node. I'm going to assign an index to the node because I want this graph to store anything, any type A, but I need to be able to work with those types. So what I want to do is assign each node some unique index as an integer, and then everything with the graph is going to work with those indices. So everything with the graph is working with strictly ints, and then whenever I need to take a node's ID and look up its actual value, like what's stored at this node, I'm going to look up this map of nodes and say, what's the value at this index? And that's going to give me the original A back. So this graph will be a graph of strings. Each one of these nodes will receive an ID. And when I add a node, I'm going to give each node an ID. When I add that specific, like UCLA, SRI, to the graph, give it an ID, and then I'm going to add the edges by the IDs. So if I say UCLA is ID 0 and Stanford is ID 1, and I want to add an edge between UCLA and Stanford, I'm going to add node 0 UCLA, add node 1 Stanford, and then add edge 0 1 or 1 0. When I add a node, it's going to add to my nodes list. That index is now associated with that value. And then I'll initialize the adjacency list to be an empty list. It has no connections yet. Whenever I add an edge, I'm going to add to the adjacency list that index mapping to the new index and preserving everything that was in the adjacency list before. And I'm going to add the edge in the other way. Every edge is in the adjacency list twice for each side of the connection. So like UCLA to Stanford, UCLA to Stanford, Stanford to UCLA. Every edge is represented in an adjacency list twice. Specifically because this is an undirected graph. So every node, every edge is technically two edges because it's an edge going from UCLA to Stanford and an edge going from Stanford to UCLA. Little secret, undirected graphs actually don't exist. They're just directed graphs where every edge exists. If it exists, it also exists in the opposite direction. There are technically two edges mathematically. So, and if that's the case, then we call it an undirected graph. So I'm going to add both directions of the edge each time an edge is added. And I have a way to look up the initial value, the original underlying value for any node. When you're looking at the project code, I have a specific function to generate these IDs for any grid location. And you can look through my provided code and see what that function is. And if you use that same function, you can look up an ID. You can, given any grid location, you can compute its ID and then look up that specific node in the graph. So I do have a little structure built into the indices in the graph that I give you for the homework. So take advantage of that. Did I change it from programming to English? Yeah, I did. So I realized that I had it tagged as basic programming because I just thought, oh, it's like basic programming. Then I realized basic programming was the programming language BASIC. And I couldn't find a just general programming. I don't know why I added English. Just because, I don't know, probably because I speak English. That doesn't mean I'm teaching English, does it? I don't know how these tags work. I don't know. So that's the code to represent a graph. Tag just means speaking English. Cool. I don't know if the tags really matter for something like this. Regardless. And then to use this, I would add all my nodes. I'll give each node an ID. Here I'm just doing it randomly not really randomly, it's just in the order that I had them in the previous slide. Give them unique IDs. It's just important that when you assign these IDs that they are unique. I can't reuse one of these numbers and expect things to work. Everything will just break after that. And then I'm going to add every edge in this graph, every edge that we saw in the previous slides. I'm going to add those by ID. So like add edge 4, 6. This means there's an edge between RAND and SDC. This 12, 10. That means there's an edge between Case and Carnegie. In this graph, I don't do anything with it in this method. This is just this program. It's just an example program. But graph, after all this is called, contains all of the information of the graph that we've seen on the previous few slides. There's no Scala tag, unfortunately. Flipping the parameters of add edge would not change anything because I treat these as symmetric. If it's 1 and 2, if you reverse these, like these two lines are still going to do the same thing, just in reverse order. It's going to have the same exact effect, just because of the way that I coded this. These two lines are exactly the same, except the 1s and 2s are swapped. So if you swap the parameter order, the argument order here, it's going to be fine. And that's why I intentionally have this 12, 10, and the 11, 8. I have these intentionally backwards just to show that off, just to prove that point. I should have more of them backwards, actually, just to really hit that point home. I'm a bit confused on edge, but I don't know where. So every time we have a connection between two nodes, that's an edge. So there's an edge between SRI and Utah in this actual underlying data of the internet. So there's an edge between SRI and Utah in our graph, representing that physical connection in the internet. So this graph is representing this version, this old, what the internet used to look like before it was called the internet. Back when it was ARPANET, I believe, ARPA or DARPANET. I don't remember what stage of the timeline this exact image is at. And then in our code, so this is all visual. We can't, like, our code doesn't understand, unless we code up pattern recognition, machine learning algorithms and vision processing, image processing, and all that. We're not doing that. So we need to have some data structures to store that information. So instead, we're going to store those edges in an adjacency list. And we're going to say any node by ID, we're going to have a way to look up all of the nodes that it's connected to via an edge. So that edge, what edge did I pick? SRI in Utah, is in this adjacency list by saying SRI is the node 2, Utah is the node 5, and I'm going to add the edge 2, 5. This right here is adding that specific edge between SRI and Utah to this graph. And now in your code, when you have a node, you have a specific node by int, and you want to look up all of its, what we call neighbors, all of the nodes to which it's connected via an edge, you go to the adjacency list and say, hey, adjacency list, look up the list of ints for 2, where 2 is SRI. And then in the list that's returned, we say, does that list contain 5? That would be asking the question, is there an edge between SRI and Utah? And the answer should be yes. How does it know 2, 5 is an edge? So we add it here. That's going to add it to the adjacency list. In both the list, so the adjacency list will have a list for 2 and a list for 5. No matter what we look up, we say adjacency list.get 2 or .get 5, or rather just the parentheses, the syntax I think most of you have been using. 2 or 5, that's going to return a list of ints And if I get the list for 2, it's going to contain 5. If I get the list for 5, it's going to contain 2. Does it return 2, 3? I believe. For 5, what example were we using? We were using Utah, right? It'll be SRI, SDC, and MIT for Utah. So if we get a 5, it'll be 2. I keep forgetting. SDC. It'll be 2, 6, and 7. That'll be the list that's returned. If we get the adjacency list for 5. It'll return all the nodes to which it's adjacent, or all the nodes connected by an edge to that node. If we get it for 2, let's do another one. I don't want to do that many. Let's get it for Stanford, UCLA, and SRI. If we say, hey, adjacency list of 1, that'll return a list containing 0 and 2. Because those are the 2 nodes to which the node 1 is connected. How does it know when one of the nodes is adjacent? Because we called add edge to add those edges. It's similar to key value map. I mean, we are using maps to represent this information. So in that sense, yes. We're combining maps and lists. So we're starting to combine our existing data structures to form new, more complex data structures. We represent the data structure of a graph using maps and lists. Or at least I am in this specific implementation. The theory of an adjacency list is always going to stay the same, but in other courses you might see different data structures in the implementation to represent that adjacency list. I'm using a map of ints to a list of ints to represent our adjacency list. So I needed a sequential data structure and a key value store to represent a graph. A lot of times you'll see a map of ints to linked list. Oh, this is a linked list, I guess. I think this is the most standard way to represent an adjacency list. A key value store with a linked list as the values. All right, let's define what a path is. This is very important for the homework. What is a path? A path is a list of nodes where each consecutive pair of nodes is connected by an edge. So like this is a valid path in this graph. UCLA to SRI, they're connected by an edge. To Utah, connected by an edge. MIT, connected by an edge. BBN, connected by an edge. To RAND, connected by an edge. So this is a valid path in the game because you can travel from UCLA to SRI to Utah to MIT to BBN to RAND. In the old days of the internet, of ARPANET, this could be a valid path that a packet can travel to get from UCLA to RAND. That's a valid path. There might have been many packets that actually took that exact path through this prehistoric internet back before. I think that was before humans were even recording anything and did not have any technology. This is what the internet used to look like back when they were still like fighting dinosaurs and living in caves. This might be how a packet traveled through the internet. Just to be sure, that's a joke. I don't want somebody saying Jesse thinks the internet. And this is not a path through this old network. SRI to Utah, there's an edge connecting them. To BBN, there's no edge connecting these two. So this is not a valid path in the graph. The length of a path is the number of edges connecting it. Do I really not have a slide on distance? I guess I don't. The length of a path, or the distance between two nodes, actually no, I do, but it's on Wednesday's content, is the number of edges between it. So UCLA, SRI, Utah, this path here, this is going to have length 1, 2, 3, 4, 5, which is equal to the number of nodes in the path minus 1. Wonder what kind of YouTube videos during the dinosaur time is. Yeah, it was the quality was pretty low on those. They actually did record them on potatoes, fun fact. So let's talk about breadth first search quickly. We'll talk about breadth first search much more in depth on Wednesday and applications of it. But let's at least introduce breadth first BFS. We're gonna introduce BFS today. I said it right like one of the first times. I couldn't do it again though. So there's a few reasons to run breadth first search. One reason is to find the connected component of a graph. I want to know if given two nodes in a graph, are they connected? Breadth of the wild search. I like that one. Are these two nodes connected in the graph? There's one question we can ask. So given two nodes, are they connected? Well, they are if there exists a path between them. Like for this graph, this is a fully connected graph. From every node, you can get to another node in the graph. And that's in fact what we want from the internet. We want from any machine connected to the internet to be able to communicate with every other machine connected to the internet. That's what we want in this specific example. We want a connected component. If a few of those lines are severed, maybe if the power goes down at a router or somebody's digging and cuts a cable, we might have a few severed connections here. Now this is no longer a connected graph, and we want to ask ourselves the question, given two nodes, are they connected? Can I send a message from UCSB to Carnegie in this graph, with this graph? It's a question we like to ask in computer science. We want to know that for various data represented by a graph. So admittedly, that's a super easy problem to solve with this graph. We're just going to look at it. We're not going to even bother training a computer to do that. We're just going to look at this graph and be like, well, these nodes are not connected to these nodes. But here's what the internet looked like, I believe in like 2005, like a while back. Here is what the graph looked like back then, where these are IP addresses, and I believe it's links. If an IP links to another IP address, I believe that's what this one is representing. And it's a lot harder to visualize if this is a connected graph or not. What's the connected component of this graph? Is this little cluster here connected to everything else outside of it? Is this node connected to this node? Is there a path between those two? Well, that's a bit harder to find out. And other questions that you have, any questions you have about this data, you're not eyeballing that. You're not just counting. What's the distance between this IP and this IP? I don't know. I'm going to write a computer program to figure that out for me because I don't feel like doing it. So to answer this question and other questions, we're going to use this for pathfinding as well. We're going to use breadth first search this time. BFS. I miss that D sometimes. BFS. And for BFS, what we're going to do is choose a starting node. I'm going to choose this one because it's visually on the top. I'm going to go to the adjacency list, and I'm going to say that I explore this node. And now I'm going to go to the adjacency list, look up all of the nodes that are connected to this node, and explore all of those nodes. Then all of the nodes that I just explored, I'm going to look all of them up in the adjacency list, and I'm going to explore all of their neighbors. Any node connected to any of those nodes, I'm going to explore all of those. And then all the new nodes that I just added, I'm going to explore all of their neighbors too. I'm going to look up them in the adjacency list. Utah and SDC, the ones we just added, I'm going to look up all of their neighbors and explore all of them as well. Once we do that and we have a round where no new nodes were explored, I'm done and I found the connected component of the starting node. So I have all of the nodes that are connected to UCLA. In a nutshell, that's breadth first search. Looks like neurons in a brain. It's a very deep comment. We could talk about that. The internet, it kind of is a giant brain. It's crazy. It's wild. Do you mind saying that last part again? So if we start at one node, explore all of its neighbors, explore all of their neighbors, explore all of their neighbors, and keep repeating this process until we don't explore any new nodes. Then all of the nodes that we've explored are the nodes that are connected to the starting node. And we've in fact found one of what we call the connected components of the graph. All of these nodes that we explored are connected to each other because we found a path between them. And any node that we didn't explore are not connected. There's no way to get from UCLA to any of these nodes because we didn't find it in our breadth first search, our run of the algorithm. If you wanted to find all of the connected components, you would pick any node that you didn't explore and rerun the algorithm again. Just pick any one of these nodes, rerun the algorithm. BNN is going to explore MIT and Harvard, going to explore Lincoln and Carnegie, going to explore Case, then going to explore no new nodes, and then that's the other connected component of this graph, which happens to have two connected components. What kind of Brad are we searching for? And one way that looks is like this. This is, I removed this explore data structure. It was causing too much confusion, too many questions in office hours. From the code that I give you. But I do give you an example of BFS. And it looks similar to this at the very least. So we're going to start with an explored set of nodes, which is only the starting node. Oh, actually, no, I don't have any extra in here. I leave this data structure in there. There's another data structure called distance that I removed. And I'm going to have a queue of the nodes that I'm about to explore, that are queued up to be explored. I'm going to queue up the starting node. And while there's still something left to explore, I'm going to explore that node. So I'm going to dequeue that to get it out of the queue. Whatever node's in the front of the queue. I'm going to look up the adjacency list, look up all of the neighbors of this node. And for each neighbor of that node, if that node has not been explored, add it to the mark it as explored, adding it to this set, this explored set, which again from 191 doesn't allow duplicates, and which doesn't matter because I'm checking if it's in the thing already anyway. I could get rid of this conditional and just add it, and then conditionally add it to the queue. But in the queue, add it to the queue. If it hasn't been explored, add it to the queue so we make sure we check all of its neighbors. Keep going until the queue is empty, and we'll do exactly what we said on the previous slide. Could we make an oven that uses through BFS ingredients? You could. So if you don't check if the node has been explored already, you're going to get the problem that I mentioned with the tree algorithms. You're going to enter an infinite loop and just keep exploring the same node over and over and over again. I don't know if this joke's worth it, but I'm committed now. It's going to just keep looping over and over. This will never be empty because you're going to explore a node, add its neighbors to the queue, explore its neighbors, add that original node to the queue, and you'll keep iterating over and over. So if you run that enough, it could get hot enough to actually bake some bread. We're so funny here. So if two nodes are connected, they're connected if, when you're running BFS, start at one of the nodes, and if you ever explore the other node, they're connected. The old lecture question was, given two nodes, check if they're connected. That's why I have that connectivity thing. All right, with that, peace out, YouTube.